the product closed. So the product, we know that the product of two natural numbers is also natural. So this we will say star is so we were discussing groups. So we say we were discussing groups today. We have just started. We were discussing groups. So group is I will do a recap. Group is a pair consisting of one non-empty set and one binary operation which is closed under that set. So you take one element from that set, another element from that set, compose them under the binary operation such that you get a result that is also a member of that particular set. So this a binary operation defined like g by g going to g and a non-empty set g such that the following axioms has to be fulfilled. One is it has to be associative, that is a star b, a star b star c is equal to a star b star c. So the order of operation is irrelevant. Second is that it has to have a neutral element. That is, star has to have a neutral element such that if you compose that neutral element with the A, you get the element back. So like A into 1 is A, like that. And next is it has an inverse element such that if there is an A, for all A, there exists a B such that A star B is equal to that neutral element N. So, is now we are asking the question, is natural number comma star a group? So the first thing we will check is whether it's closed or not. And the product of two natural number is closed. So star is closed under N. Because the product of two natural numbers is always a natural number, guaranteed. Next, associative. This is also true. Multiplication is associative. So this we can directly say it's true. Multiplication by its nature is associative. Next is existence of neutral element, or as you say, existence of identity. Neutral element is usually not the preferred term. The preferred term is identity. Now what is the identity of multiplication? 1. 1, there exists 1 which belongs to n such that a star 1 is equal to 1 star a is equal to a. So there is an existence of identity. Next, so this is true, closed is true, associative is true, identity is true. Last we have to check existence of inverse. Now this is where things can go wrong. See, let us take for all elements it has to exist. So we can take any one element, and if it exists, if it does not exist, then we can say it does not exist for all. Because if it does not exist for one, then anyways all condition is not satisfied. All means every one of them, every last one of them has to satisfy, which is will not be the case. Let's say 2. 2 belongs to natural number, but a star 2 equal to 1, if you solve, you will get a equal to half, which a is equal to half, which we know is not natural. So some elements, at least one element, we cannot say all element, but we can say at least one element doesn't have inverse. So existence of inverse is not satisfied implies a natural number under multiplication is not group. So what can be a group? Rational numbers can be a group. Why? Because rational numbers are of the form p by q. So if, let's say, now take another group, rational numbers under multiplication. So we take rational numbers q under multiplication. Is this a group? One, closure. Of course, the product of two rational numbers is a rational number. So yes. Associative. Multiplication is always associative. So yes. Next, existence of identity. So how does a rational number look? P by q into 1 will give you p by q. So yes, identity exists. Now, hmm. So very good. So rational number multiplication. Now we have to find R1. There exists R1 equal to P1 by Q1. So this is one rational number which belongs to the set of rational numbers. Now P1 by Q1 into 1. If you solve, equal to R2. No, sorry. P1 by Q1 into R2 is equal to 1 if you solve. Then R2 becomes Q1 by P1, which is still a rational set, provided P and Q are not 0, which is the definition of rational number. So rational number, but this has to be 0. So you can say Q star is group subject to P not equal to 0, Q not equal to 0, where P by Q belongs to rational number set for any, for all P by Q belonging to the rational number set. So as long as P and Q are not 0, it is a group. But if one of them P and Q is 0, then it is not a group, because the existence of inverse is no longer satisfied. Now, a group is abelian if it is commutative. That means a group is abelian if it is commutative. That means A star B is equal to B star A. So if you do A star B like A into B, then it is equal to B into A. So the group involving multiplication, of course, is abelian, because the multiplication of two natural, rational, real, whatever numbers can be done in any order. So we can say that it is an abelian group. But what might not be an abelian group? Matrix multiplication. Matrix multiplication is not commutative. A matrix into B matrix is not equal to B into A matrix. So that concludes group. Now we will come to field. Now field definition is usually derived from group. Group is like the fundamental unit. Field comes from there. So a field is a triple. So now we have two binary operations. Group first defined under one binary operation. Field is defined under two binary operations. So a set F consisting of at least two elements, of course, because if you do not have two elements, you cannot do binary operation. Next, a binary operation F plus closed under F, which is called addition, and a binary operation dot closed under F, which is called multiplication. So you need two binary operations and one non-empty set. Now, such that the following axioms are fulfilled. So the following axioms have to be fulfilled: that F plus, F and plus, so this binary operation, addition binary operation and the set, has to form a abelian group. It forms a abelian group means it is associative, it has an identity, it has an inverse, and it is commutative. So F plus has to satisfy four properties, whereas F excluding the identity under multiplication is also an abelian group. That is, multiplication, of course, you have to exclude the identity. So of plus, not the identity of multiplication, but the identity of plus, because the identity of plus is 0. So you have to exclude 0 in the multiplication group, or else, like here we have said, or else we will have division by 0. So the addition group is abelian group without any asterisk, but the F without the identity and binary product is an abelian group. So for constructing the abelian group of the multiplication, you have to exclude the additive identity, not the multiplicative identity, but the additive identity. And next, the third axiom that it has to satisfy is that multiplication distributes over addition. That is, A into B plus C is A into B plus C is equal to A into B plus A into C. So if all of these are satisfied, like usually in the set of real numbers, if you take the normal addition and multiplication, so what will be the additive identity? 0, because if you add 0 to a real number, you get the same number back. Whereas the multiplicative identity will be 1, because if you multiply with 1, you get the same element back. And of course, the real number, real without 0, so real and positive, real and addition, real number set and addition will form an abelian group, whereas real number without 0 and multiplication will form another abelian group, and multiplication we know will, for real numbers, distribute over addition. Same goes for this rational number and complex number. Okay, but not natural number. Why? Because natural number n set, if you take the multiplicative inverse, it goes outside the group. That cannot, because 2 you take half, so you have to include the fractions. So the minimum you can do to include the fraction is take rational number. Natural and whole numbers do not form fields under these operations. Now we come to the third concept, which is called ring. Just give me 2 minutes, I will take some tea. I'm feeling drowsy. Yeah, hello. Now, where were we? So in a field, we got that F plus has to form an abelian group. F without the additive identity and multiplication has to form an abelian group, and multiplication should distribute over addition. Now we come to another concept, ring, which is nearly a field. So it is not, field is all encompassing. Ring is below that. Ring is smaller than that. Group is the smallest. So ring is nearly a field. The only thing which is missing, that we do not require the multiplicative structure to have inverse elements. So a commutative inverse unitary ring requires that E plus, the element E, the set E and plus has to form an abelian group, just like a field. And the E dot has to form a commutative monoid. What is commutative monoid? So it is an abelian group, but you take this axiom out. So abelian group, what is there? One is associative, one is neutral element or identity. This is also known as uh, yeah, a neutral element, or as it is called in Indian textbooks, identity. And the inverse element has to exist for a group, but for a monoid we do not need this. Monoids don't need axiom 3, and it has to be, if it is has to be abelian, then it also has to satisfy commutative property. So a ring is ring, in ring E plus, the set and plus will form an abelian group. The set and dot will form an abelian group minus the inverse axiom. So out of 4, it has to satisfy 3 of the abelian group axioms, and that is known as an abelian monoid. Not an abelian group, but an abelian monoid. And multiplication distributes over addition, which is common. So that is a commutative unitary ring. Now if you remove from E dot the commutative part, then it is only an unitary ring, not commutative. And if you remove the identity part, that is, you remove this part, where did it go? Yeah, you remove this part and you remove this part. Inverse is already gone. Then you remove this, only associative remains. Then that is just a ring, a bare basic ring. And you can add unitary and commutative on top of that. Unitary means one exists. That is, the multiplicative identity exists. That's why it's called unitary. So one exists in this group, in this ring. So usually the ring that we need is commutative unitary ring. Okay. Now we come to the modulo operation. So what is modulo operation? Modulo operation means basically you divide an A mod P. B is congruent to A mod P means if you divide A with P, you will get B as remainder. So denote this tilde n as the equivalence relation modulo n. That is, if A tilde n B is true, then what happens is that A minus B is equal to a product of a multiple of basically this mod n. A minus B is, so 0 is congruent to A minus B mod n. This is how you write this relation. Means if you divide A minus B with n, you get 0 remainder. So This is called A is equivalent to B. Equivalent to B modulo N. Write this definition, it's important. If and only if 0 is congruent to A minus B modulo N. So let's say 3. Okay, denote Zn the set of all equivalence classes Xn modulo N. That is, for n equal to 3, you have to find all the elements that are equivalent to 0 modulo 3. What does that mean? So this 0, this thing is important, equivalence class. So see, Zn is the, let it go, set of all equivalence classes. So it is a set of sets. Set of all equivalence classes modulo n. So 0, that means classes x modulo n. X modulo n. So here we have to find the set of numbers for which a minus 0 mod n will be congruent to 0. That is, it will leave no remainder. That is, n perfectly divides a minus 0. So we have to find all numbers such that n perfectly divides a minus 0. So here 3 perfectly divides a. If 3 perfectly divides a, what does that mean? It means it's just the multiples of 3. So on both sides, if you take, center will be 0 because 0 modulo 3 is 0, and this will be 3, 6, 9, because 3 modulo 3 is 0, 6 modulo 3 is 0, 9 modulo 3 is 0, because dividing by 3 for any one of them will leave remainder 0. Next, from here, basically the mirror image, minus 3, minus 6, minus 9, and so on. So this is the equivalence class of 0 modulo 3. Now we find the equivalence class of 1 modulo 3. How to find that? Is such that this means n perfectly divides a such, find a, basically the task is to find a such that n perfectly divides a minus 1. So we have to find all numbers such that if you subtract 1 from them, you get multiples of 3. So what is the equivalence class of 1 modulo 3? It is 1, 4, 4 minus 1, 3, 5. Basically, you just add 4, sorry, not 5, 7, 4, 7, 10, 13, so on. And then you do a mirror image. Minus 2, minus 2, no, not mirror image, sorry, minus 2, then minus 3. Minus 4, no, sorry, minus 4, no, minus 5, and so on. So minus 5, minus 2, 1, 4, 7, 10, 13, so on. Like this. This is the equivalence class of 1 modulo 3. Okay. So now we have defined the set like this. Now 2 modulo 3 is same, but when we come to 3, because this is modular arithmetic, there are only 3 elements, 0, 1, 2. We don't need to come to 3. Okay. So 0, 1, 2, we come to, we satisfy till 0, 1, 2, and that is the equivalence operation. Now, we have to define Zn operations. Now this Zn set is basically the set of all 3 sets. It is the set of sets of 3 uncountable sets. Now, define Zn operation such that An plus Bn, so the equivalence class of 0 and the equivalence class of 1, if you add them, so you add them manually, you will get what? 0, yeah. Yeah, you add them and mod them. Basically, this plus is basically modulo. So you add them and mod them. So minus 6, minus 5. You add them, minus 11. Minus 11 modulo 3. So it is minus 11 modulo 3 will be, what will be the remainder? Minus 2. Yeah, so minus 2. Like that, this one will be minus 3, minus 2, minus 5 modulo 3. So okay, let's do the positives one. So 0 plus 1, 1 modulo 3 is 1. 3 plus 4, 7. 7 modulo 3 is 1. 6 plus 7, 13. 13 modulo 3 is 1. No, something is going wrong. Okay, sorry. So here we don't have to add like this. What it has defined is we are defining these operations. We are not validating this operation. We are defining this operation, that there is an operator called plus modulo n, which adds these two equivalence classes, and the result is defined to be 0 plus 1 modulo 3. So if you add this and this equivalence class, so 0 modulo 3 and 1 modulo 3. If you add 0 modulo 3 and 1 modulo 3, it is defined that this plus is a special plus, such that you will get 0 plus 1. This is the normal arithmetic plus modulo 3. So 1 modulo 3. Similarly, if you have 1 plus 3, sorry, 1 plus 2, 1 modulo 3 modulo plus 1 plus 2 modulo 3. This will be 3 modulo 3, which is basically 0 modulo 3. Okay, like this. So this is one operation we are defining. And another operation we are defining is that the product of these two equivalence classes is basically the product of these two integers modulo 3. So 0 modulo 3 into 1 modulo 3 is 0 into 1 modulo 3, that is 0 modulo 3. Similarly, 1 modulo 3 into 2 modulo 3 is 1 into 2, 2 modulo 3. 2 modulo 3 into 0 modulo 3 is again 0 modulo 3. So we see they are closed. You take any two of them, 3 ways, you take any two of them in 3 ways, you will see that the result is one of these 3 only. So it is a closed operation. Okay, so like this, 3 modulo 7 and 2 modulo 7 will give 5 modulo 7, 4 modulo 7 and 5 modulo 7 will give 9 modulo 7, which is basically 2 modulo 7. So This is a this Zn with these operations is a ring. Okay. Now when does this ring become field? If n is a prime number, it becomes field. So that is the theory of field and ring. So if you take the equivalence classes of a number modulo of a number modulo number, then you define two operations such that a modulo n plus b modulo n is equal to a plus b modulo n, and a modulo n into b modulo n is equal to a into b modulo n. If you define like this, then you have defined a ring. But if that number, generator number, that n is prime, then you have that ring is actually a field. So ring is like additional conditions on ring. If you impose, then it becomes a field. Okay, so that is the definition of the, yeah. Okay, Bézout identity is not needed. Modulo division, I think, is also not needed. Okay. Now we will take a brief detour. Now that we have defined group, ring and field, we will take that brief detour and we will study polynomials. And then eventually by combining these two, we will go to Galois field. Okay. So now we will come to polynomials. What is a polynomial? Polynomial definition I don't need to provide. It's basically expression containing various terms which are powers of a single variable. Okay. So yeah, now let f plus dot be a field. So we are defining a field f under the operations addition and multiplication, plus and dot. A polynomial of degree d with coefficients in f. That is, the polynomial has a degree d. So x to the power d plus x to the power d minus 1 plus up to 1. Okay, like say if it is 3, then x cube plus x square plus x plus 1 with coefficients in f is an expression of the form ad into x to the power d plus ad to the power ad minus 1 x to the power d minus 1. These ad minus 1 all are in x, all are in all are in the set f. And d is a natural number excluding 0, then, and x is a symbol. Okay, so that is the polynomial definition. So we have defined the polynomial over a field. Now if there is a field, that means there is addition, division, multiplication, and this addition multiplication has to be suitably defined. So addition means you simply add the coefficients, and multiplication means you take a dot product of the coefficients. So here you take the double summation dot product of the coefficient. A quotient ring. Okay, these we don't need. Okay, irreducible polynomial. Now we know what is a polynomial. Now we will come to irreducible polynomial. So a polynomial over a field is called irreducible if the only divisors of the polynomial are a into a dot p and b with some ab belonging to f. That is, either the polynomial itself is dividing the polynomial, or it's just getting divided by a single number. It is not getting divided by a sub-polynomial. So that is the thing with a irreducible polynomial. So it is either, if it is a degree d polynomial, it must be only divisible by the polynomial itself and a degree 0. So by a degree d polynomial and a degree 0 polynomial. So there should not be any factors which are polynomials of degree d minus 1 up d minus 2 up to 1. So the only factors can be the d and degree d polynomial and degree 0 polynomial. So only factors of a degree d polynomial are a degree 0. What is a degree 0 polynomial? Basically a scalar. Degree 0 polynomial, I'm writing bracket means scalar, and a and a scalar multiple and a degree d polynomial, bracket में the polynomial itself. Recall the definition of a prime number. What is the definition of a prime number? Can you tell? What is the definition of a prime number? What are the factors of a prime number? The factors of a prime number p are the prime number itself, p, and 1. So p and 1 are the only factors of a prime number p. Similarly, a irreducible polynomial, basically you can relate, it is like a prime polynomial. Okay, so like what is prime numbers to number theory? Irreducible polynomial is to abstract algebra. So it is like a prime number. It is like a prime polynomial. So it only has two factors. One is itself and another is a degree 0 or 1 basically. Now for a field f and an irreducible polynomial p, the quotient fx by L with L equal to the quotient fx by L with L equal to lambda into p is a field. So lambda into p is basically a scalar multiple of p. So the quotient for a field f with and an irreducible polynomial p, the quotient of any polynomial with respect to this with respect to this polynomial p is a field. So if you remove all this if you remove all these multiples of the irreducible polynomial p, then you get basically a field. Okay, now we will come to Galois field. So the Galois field, the characteristic of a field f plus dot is the smallest number c such that n plus n dot plus n dot plus n dot c times is equal to n plus. So the characteristic of a field is the smallest number by which you have to add, by many times you have to add the multiplicative identity to get the additive identity. Okay. So this is known as the characteristic of a field. If no such number exists, then the field is said to have a characteristic 0. Next is the order of the field. The order of the field is basically the number of elements in the set F. So the number of elements in the mother set of the field is the order of the field. And if the order is finite, that is the mother set only has limited number of elements, then if the mother set only has limited number of elements, then it is a finite field. And this finite field is in another name known as Galois field. So Évariste Galois was a French scientist by whose name this field was named. So finite, basically any field which has finite number of, any polynomial field which has a finite number of finite number of elements is a Galois field. Okay. So this is Évariste Galois. And he died at the age of 20. So he did all this Galois field algebra before the age of 20. So despite his early death, he is probably the most influential researcher in the field of algebra in his century. Okay, so that was just a brief aside. Next, these are some proofs. Okay, so order, yeah. So now we have this. Now recall a this set plus dot. This was only a field. This was a prime. This was a ring. Only this ring became field when p was a prime number. Okay, so Galois field always has to be generated from a prime number. Now that's why you will not get GA, like it is either prime number of or power of a prime number, like GF4, GF5, GF2, GF3, GF4, GF5, because they are prime or power of prime. Okay, but not GF6, because GF6 is neither a prime nor the power of a prime. So GF6 doesn't exist. Now, is there any doubt up to now? Is there any doubt? Please do tell. I will be happy to explain again. Okay, so now we will need, if there are no doubts, then we will go further into the details of Galois field. Okay. Mm, mhm. Yeah. So the properties of Galois field are that, because another name of Galois field is finite field, so the number of elements is finite and it is determined by the prime number p. And next is the Galois field is closed. Of course, any field has to be closed under both addition and multiplication operation. Next, Galois field is commutative. Field is commutative. So Galois field is also commutative under both multiplication and addition. And it is also associative under both multiplication and addition. Next, the another fundamental axiom of field is that the multiplication has to distribute over the addition, which is also true for Galois field. So points 2 through 5, 6, 7, only apart from 1, 2, 3, 4, 5, 6, 7 are essential properties of field, and Galois field is also a field, so it also has to satisfy the properties of a field. Now, hmm, the order, so what are the, now we have some, so the Galois field only exists for a prime number or the power of a prime number. Straight power, not composite power. So 2 to the power something or 3 to the power something, but not 2 to the power something into 3 to the power something. So not 6, not 12, not any of those. Now, for every prime power p to the power k, there exists a field of order p to the power k. All fields of order p to the power k are isomorphic. That means all of the fields that you can derive from a particular p to the power k, particular 2 to the power 2 square, 2 cube, like that, all of the fields are isomorphic, means all of them are identical except for substitution. That means if you substitute properly, all of them will become identical. Their basic structure is same. Okay, so maybe one time you you define with rational numbers, one time you define with maybe some alphabets, but they are essentially the same. You are just assigning symbols according to your convenience. That is called an isomorphism. Next, all fields of order p to the power. Next, the characteristic of the finite field of order p to the power k is p. So what is characteristic? Characteristic is the number of times you have to add the multiplicative identity to get the additive identity, and that is yeah, um, that is the p. So you have to the order is, the characteristic number is p. Now we will construct GF2, Galois field of 2, the prime number 2, and then we will see whether all these axioms and properties and theorems are holding or not. Okay. The Galois field of order p to the power k is uniquely defined by the value p to the power k. That means if the Galois field, if you say that give me the Galois field of 2 square, so the Galois field of 2 square is unique. It is different from Galois field of 2 cube, but there are no two Galois fields of 2 square. So if you say 2 square, that means they are Galois field of that is a particular field. So you don't need to specify for any further parameter, because Galois field of 2 square means the Galois field of 2 square. It does not need any other specifier. Now, and it is given by the set this 0 1 x square x cube, means it is given by a polynomial. And it is, how do you construct that? You basically take any arbitrary irreducible polynomial in that set. So any one of the polynomials, there are a finite number of irreducible polynomials in a particular set. So you have to, in a particular field, so you have to take any one of them. Because Galois field is unique, if you derive by any one of those polynomials, you will get back the Galois field uniquely. That means if you take polynomial of p1, you will get the Galois field. If you take polynomial p2 also, you will get the same Galois field. So the choice of the polynomial doesn't matter. You just have to find an irreducible polynomial, and that's it. Now, let's say Galois field of 2. So Galois field of 2 means it has to be closed under addition and multiplication. So it is identical with the prime field Z2. So Z2 means, what does Z2 mean? Z2 means we have to find the equivalence class, like we have said, 0 2. So what are the numbers that give 0 modulo 2? What are the numbers that give 0 modulo 2 within this closed field? Means it cannot exceed 2. So equivalence class. And what is this definition? This definition is, you have to find a number such that a minus 0 mod 2 is 0. So what is that number? 0 only. And 1, is, so you have to find a minus 1 mod 2. So if you take 1, you will get 0. 0 mod 2 is 0. But if you take 0, you will take 0 minus 1. So minus 1 mod 2, that is minus 1. So it does not hold true. So 1 is 0 and 1. So Z2 is basically equal to 0 and comma 1. Now you have to define two operations, plus 2 and dot 2, such that they are closed, associative, commutative, distributive. and the multiplication must distribute over the addition. Okay, so like that. So plus you define like modulo addition. 0 plus 0 0, 0 plus 1 1, 1 plus 0 1, and 1 plus 1 is 2. 2 modulo 2 is 0, so 1 plus 1 is again 0. Now this what is this table called? What is this gate? Can you tell the gate? What is this gate? This is nothing but the XOR gate. It is an inequality detector. If the bits are unequal, it gives 1. If the bits are equal, it gives 0. Now, under dot 0.00, 0.10, 0.10, 1.1, 1. So this is what? The what gate? It is AND gate. So the addition under GF2 is basically XOR, and the dot product under GF2 is AND. So basically it is isomorphic with the 0 1 set, XOR, AND. So GF2 is nothing but the Boolean variables 0 1. Now we are saying Boolean variable, but we can also say integer 0 1. So that is isomorphism. Yours, this thing, GF2 is basically this, defined in numbers, integers. But you are defining in terms of booleans. This is boolean. But they are the same set. They have the same structure. But their symbols are different. You are interpreting differently. So GF2 and this is not equal. They are basically, the correct term is isomorphic. So GF2 is isomorphic with the structure 0 1, XOR, AND. Okay. Next, GF3. GF3 is basically the prime field of equivalence class 3. So here you will do 0 plus 1 0. So plus will simply be modulo addition. Okay. So 0 plus 1 0, 0 plus 1 1, 0 plus 2 2, 1 plus 0 1, 1 plus 1 2, 1 plus 2 3. 3 means 0 again. So this is basically mod 3 addition. This is mod 3 addition. And what is this? This is basically multiplication mod. This is A dot B mod 3. So you take the product. If it is below 3, it is that product value only. If it goes above 3, which it goes here, 2 into 2 4, it means 4 mod 1, 4 mod 3 3, 4 mod 3 1. So finite fields are unique. Now GF4. GF4 is not, 4 is not a prime number. So GF4 is not a fundamental field. It is not a prime field. GF4 is basically GF2 square. GF4 does not exist. GF2 square exists. Now they are same, but they are different, constructed differently. So if it is a plain prime number, you just do modulo addition and modulo multiplication and you will get the field. But when it is GF4, GF9 like that, then you have to work out some unique ways. Okay. So the elements will simply not be 0, 1, 2, 3 and you do mod 4. For prime number, you just do up to n minus 1 you take, and then you do modulo addition, modulo multiplication, you have your field, Galois field. Fine. But for prime powers, not primes, but prime powers, you have to take A and B, and you have to gradually fill. So first is 0. We can fill the rows and columns that have 0. That is very easy. Addition means you add something, you will get back that same element. So you just copy them. 0 1 AB, add with 0, you get 0 1 AB. 0 1 AB, because 0 is the additive identity, right? Similarly, multiplication, if you do 0 into 0, it is 0, or 0 into anything is 0. So first row and column is 0, that is guaranteed. Now we can also fill the row of 1. Why? Because this is the multiplicative identity. This is the multiplicative identity. So if you multiply, you will get the same thing. So 1 times 1, this 1 times 0 1 AB is 0 1 AB, and this 1 times 0 1 AB is again 0 1 AB. So we have filled this. 4 places are remaining here. The chunk of places are remaining here. Now we have to use the properties of the field and find the others. Now plus is invertible. That is, if you take this like 0 and 1, 1 and 1. Okay, so plus is invertible. In every row and column, we must find every column. Fine. So for 1 plus 1, we will choose 0. Now, why? Because we cannot do modulo 4. We have to do modulo 2. The mod value, mod p, we have to do mod p. Here comes the characteristic. Characteristic is gf p to the power k has a characteristic p. We have covered that, I think, previously. Yes. The characteristic of the finite field or Galois field of order p to the power k is p. The characteristic is not, characteristic means mod. Like we are doing a minus b mod n, right? So characteristic is basically this number. Now this number for GF2 is 2, GF3 is 3, but for GF4 it is 2. For GF8 it is 2. For GF16 it is 2. For GF1024 it is 2. It will always be 2. Okay? So 1 plus 1 if we do, we have to do modulo 2. So 1 plus 1 will give 0. A plus A again will give 0. B plus B will give 0. Fine. And now since the characteristic is here, so if A plus A, why is A plus A is 0? Because A plus A is nothing but A dot 1 plus 1. 1 plus 1 we have chosen to be 0 because characteristic is 2. So 2 modulo 2 0. So A into 1 plus 1, A into 0, which is 0. Similarly, B plus B is 0. Now multiplication table we have to fill. Multiplication table, this part was remaining. A into E, A into B, A into A into B, B into A, B into B. This part we have to figure. So what is A into A? A into A cannot be 0. It cannot be 1. Because A into A 0 means A equal to 0. But A is not 0. A is a separate distinct number, which may or may not be 2 or 3. Similarly, B times B cannot be 0. As A into B implies B will equal to 0. Similarly, A into A cannot be 1, because then it will imply that A is 1. Why it will imply A is 1? Because here multiplicative inverses do not exist. This is integers, right? So A into A will be 1 only when A is 1. Now, so A into A cannot be 1. But can A into B be 1? Then next question is, can A into B be 1? or A dot A. So what are the let's fine, let's leave A dot A. So A dot A cannot be 0, cannot be 1. Can it be A? A dot A cannot be A also, because A is not the identity. A dot A equal to A means A is identity, which is not true. A is not the identity. So this leaves us with only one possibility, that A dot A gives B. Because it has to give something, it is closed. So it has to give one of the four. And it cannot be A dot A cannot be 0, A dot A cannot be 1, A dot A cannot be A. So it has to be B. So A dot A, by the process of elimination, A dot A is B. Okay. Similarly, B dot B is A. Now what is A dot B? A dot A is B. Now we have to find A dot B. So yeah. Now A dot B. A dot B cannot be 0, as A not equal to 0, B not equal to 0. So it cannot be 0. Okay, can A dot B be A? That means, what does this mean? What does A dot B equal to A mean? That B is multiplicative identity, right? Yes or no? Mr. Suresh? Hello?
Yes, sir.
Are you following this far?
Ah, yes, sir.
Okay, okay. So basically we are doing A dot, finding A dot B. So we have found out A dot A is B, and B dot B is A by elimination. Similarly, now we will find A
Yes,
dot
sir.
A, A dot B. So again we will do elimination. Now A dot B cannot be 0, because both A and B are non-zero. Similarly, if A dot B is A, what does that imply? That implies that B is multiplicative identity. But that is not true. 1 is the multiplicative identity. So B cannot be the multiplicative identity. In any field, there can be only one identity. So, not true. So what does that leave us? A dot B equal to 1, or A dot B equal to B. Now A dot B equal to B is again false, because that will imply A is multiplicative identity, which is again not true. A is multiplicative identity. This is also not true. So A dot B cannot be A dot B cannot be B, A dot B cannot be 0. So not equal to 0, not equal to A, not equal to B. What does that leave us? Because it is closed, so it has to be something. So A dot B equal to 1. Similarly, by similar logic, B dot A equal to 1. So that's it. So that fills the multiplication table. So now we have defined the operations completely. So we have defined the Galois field, GF4. So this is GF4. Now this A and B you can write as 2 and 3. But writing it as 2 and 3 creates unnecessary confusion, because then you might someday look at it and think 3 plus 3 is 0, and 3 plus 2 is 1, and 2 plus 2 is 0. So 2 plus 2 is 0 means it is modulo 2, but 3 plus 3 is also 0, which means it is modulo 3. So it cannot be true that it is both modulo 2 and modulo 3, right? So using 2 and 3 in this context creates confusion. 0 and 1 are universal identities. Like 0, 1, apart from integers, they also have the identity, sense of identity or booleans, right? But 2 and 3 are pure numbers. And simply speaking, this looks, we can write with 2 and 3, but it will look brain damaged. 0 and 1 are neutral elements. 2 and 3 are not. So you will think later, if you do not know the context, that under what law 2 plus 2 is 0, you will think, okay, 2 plus 2 is 0 means we are doing modulo 2 or modulo 4. But 3 plus 3 is also 0. Both cannot be same, both cannot be true under the same modulo. So this looks very brain dead. So that's why instead of using this, you can use this. This and this are isomorphic. This is what we call isomorphism, where we can just substitute the symbol without changing the algebraic structure. So instead of 2, 3, we use A and B. Okay. So that is GF2, GF3, GF4. I think GF2, GF3, GF4 is good enough for you all. Okay. Now, finding higher GFs, GFP to the power K, is pretty tough. So, now we will, instead of doing filling tables, because for GFH, say, you have to fill 128 values. So that is pretty, it's like 64 for addition, 64 for multiplication. Okay, so that is so 60 128, so that is not tenable. So next we will take the help of algebra to find GF. Okay, and using that we will find GF8. We will at least try to find GF8. Okay, so to find it using polynomials, we have to find irreducible polynomial. So if we want to construct GFP to the power K, we have to find an irreducible polynomial P of degree K. So we have to find an irreducible polynomial of degree 8 if we want to construct GF8. Okay, and then we have to find the, then we have to divide that polynomial with the general Galois-Field polynomial. Okay, so there are 8 polynomials of degree 3 without coefficients, without the combination of coefficients. There are 8 possible polynomials. Okay, why? Because one will always be there. One will always be there, because if you don't take one, it will factor. It will factorize. If we don't take this 1, x cube or x cube plus x or x cube plus x square or x cube plus x square plus x, they all factorize. So they are not good candidates for finding GF, because GF has to have irreducible polynomial. So it has to have the 1. So the 1 is mandatory. So now you have x cube, x square and x. And you have, for each of them you have 2 options, either to keep it or to not to keep it. So you can keep or not keep x cube, you can keep or not keep x square, you can keep or not keep x. So 2 into 2 into 2, 8. But out of these 8, if you do not keep x cube, then you do not have a degree 3 polynomial. So again, x cube you have to keep. X cube you have to keep. So you have the option of keeping or not keeping x and x square. So how many ways? 4 ways. Understood? You keep neither of them, then you get x cube plus 1. You keep one of them, you get x cube plus x plus 1, or x cube plus x square plus 1, or you keep both of them. So x cube plus x square plus x plus 1. So the highest degree and the lowest degree, x to the power d and x to the power 0 for a polynomial of degree d has to be always kept. The rest you have a choice. So how many choices do you have? How many, if there are degree d, if it is degree d, so 0 to d plus 1 terms are there. Out of that you have to take 1 and you have to take the highest, x to the power d. So d plus 1 minus 2, that is d minus 1. So 2 to the power d minus 1 choices you have for polynomial. Out of these 2 to the power d minus 1 choices, you have to find one, any one, which is irreducible, which is does not factorize. Maybe all of them do not factorize, maybe some of them do not factorize, but you have to find one, only one, which do not factorize. That is good enough. So you can see x cube plus 1 does not factorize, neither does x cube plus x plus 1, neither does x cube plus x squared plus 1, neither does x cube plus x squared plus x plus 1. Now, x cube plus 1, now we have to see whether they are irreducible or not. So whether, like, you do not see factoring here by the naked eye, but there may be factoring latent. So x cube plus 1 of course will factorize in the Galois field, because you are thinking about factorization in the arithmetic domain, but you are not working in the arithmetic domain, you are working in the modulo domain. So in the modulo domain, some polynomials might factorize, which may not factorize in the arithmetic domain. Okay, so a polynomial p over the field f has a 0 at a belonging to field f if and only if x minus a is a factor of p, or pa equal to 0. So if you put the value a, where a is an element of the field f, in that polynomial, you will get 0. So in x cube plus 1 over gf2, Galois field 2, if you put 1, so 1 plus 1, 1 plus 1 is what in Galois field 2? 0. Because in Galois field 2, gf2, your addition is basically XOR gate. So it is 1 XOR 1. 1 XOR 1 is 0. So x cube plus 1 has a 0 at x equal to 1. So it will factorize x squared plus 1 x plus 1 into x minus 1. Or x minus 1 or x plus 1. Here x plus 1 only. Okay. So this is not irreducible. And now we have 3. So now, then there were 3. So 1 we have eliminated. Next, let's put x equal to 1 in GF2 in the polynomial x cube plus x square plus x plus 1. So x cube plus x square plus x plus 1 over GF2. So let's put 1. So this is px. So what is p1? p1 is 1 plus 1 plus 1 plus 1. So 1 plus 1 in GF2. These are, see, this is GF2. So all of them are modulo 2 addition. So 1 plus 1 in modulo 2 is 0. And this 1 plus 1 is again another 0. So it is 0 plus 0. 0 plus 0 mod 2 is 0. So p1 equal to 0 means x cube plus x square plus x plus 1 has a root at 1 belonging to f. Right? It belongs to the underlying set, where f is the mother set of Galois field 2, which is 0 and 1. And plus 2 is equivalent to XOR gate, and dot 2 is equivalent to AND gate. Okay. So x cube plus x square plus 1, x plus 1 is reducible if it has a root in the field set, in the mother set of the field, it has a root, then by factorization theorem, it has a factor at that point. If it has a, this is basic algebra. So if a polynomial has a root at x equal to alpha, that means it is factorizable at x equal to alpha. X minus alpha is a factor, right? So it will be it will have x minus 1 as a factor into something. So it is x cube plus x square plus x plus 1 is reducible. So this is also not irreducible. Next we come at x cube plus x square plus 1. You take 1, p1, 1 plus 1 plus 1 equal to 1. Okay. And you take p0, 0 plus 0 plus 1. So 1. So both of the time it is not equal to 0. So x cube plus x square plus 1 GF2 field is defined as 0 comma 1 plus 2 dot 2. So x cube plus x square plus 1 is, so both of them at both of the values it is not having any factor, so it is irreducible in F, in GF2 or in F, whichever you want, right? Whether it is irreducible in other domain, we don't care. It has to be irreducible only in this 0 1 set. So x cube plus x square plus 1 is irreducible. Similarly, you can show x cube plus x plus 1 is irreducible, but any one of them will do. Okay. So both of them are irreducible. Now GF2 to the power 3 is basically, GF8 is the term 0, x to the power 0, x to the power 1, x square, x cube, x4, x5, x6. Okay. Now, x to the power 7. Why is x to the power 7 not included? Usually if it is 8 polynomial, it has 0, 1, 2, 3, 4, 5, 6, 7, 8. Sorry, 0, 1, 2, 3, 4, 5, 6, 7, 8 terms, right? So why is x to the power 7 not present? So here they have shown that x to the power 7 is equivalent to x to the power 0. And how have they shown it? This proof you can follow, but that is not important here. So yeah, now we will divide each of 0, x to the power 0, x to the power 1, x square, x cube, x4, x5, x6 with the polynomial that we have chosen, the irreducible polynomial, say x cube plus x plus 1. Okay, so we will divide all of these with x cube plus x plus 1. So if you divide by 0, you will get 0. Means 0 divided by x cube plus x plus 1, 0. Okay. Next. Okay, so next x to the power 1 x square. So these are all smaller, so you are dividing and taking the remainder, right? Mod. So all of these polynomials 0 x to the power 0 x1 x square, they are smaller than x cube plus x plus 1. So if you divide, the remainder will just be that particular term itself, right? If you divide 2 by 7, what will be the remainder? It will be 2. Mod 2 mod 7, it will be 2, like that. So in this case we are getting all the remainders. That is nothing to say here. Next, x cube. This is where the trouble starts. So x cube is basically x cube by x cube plus x plus 1. So now here you can, what we will do is basically we will multiply to match this power. We will multiply, we will subtract the multiple of ideal generating polynomial. So the generating polynomial is x cube plus x plus 1, the irreducible polynomial that you have taken. You multiply, say, x to the power 4 to match the order. So you will get x to the power 5, x to the power 4, and x7 and x7. So x7 x7 cancel, so you get x5 and x4. Now x5 and x4 similarly you can reduce, like x squared times the generating polynomial. Again you do the same algebra, you will end up with x to the power 4 plus x cube plus x square, which again you multiply with x, you will get something like this. Then x cube plus x, this time you multiply with 1 times the generating polynomial and you finally get 1. So x to the power 7 is equivalent to 1. This is how you divide in Galois field. So when you have x cube by x, when you have x cube by x cube plus x plus 1 in Galois field, you write x cube plus 1, x cube as x cube minus x cube plus x plus 1. Now in GF2, subtraction and addition are the same thing. So x cube plus x cube will give 0, like 1 plus 1, 0. So it will be 0. And minus x minus 1 will become x plus 1. So it is x plus 1 by x cube plus x plus 1. X plus 1 is a smaller polynomial than x cube plus x plus 1. So the mod x cube plus x plus 1, the modulo, will give x plus 1 finally. Understood? So x cube by x cube plus x plus 1 is x plus 1. Similarly, x to the power 4 you will get x square plus x to the power 5 you will get x square plus x plus 1, and x to the power 6 you will get x square plus 1. Now, what you will do is, all of these you are getting, you will map them to a vector. So 0 is 0 0 0, 1 is 0 0 1, x to the power 1 means basically x square plus x plus 1. If you take, what coefficients are on? This is off, this is on, this is on, off. So 0 1 0. And what is 0 1 0? 0 1 0 is 2. Similarly 1 0 0, here x square will give 1 0 0 because 1 0 0, of course. Then x cube giving x plus 1, so if it is giving x plus 1, that means it is 0 1 1. 0 1 1 means 3. Similarly, x square plus 1 means 1 1 0, so it is 6. X square plus x plus 1, so this is 7, this is 5. So here we get the final Galois field. Now we have the encoding table. So now we will define the, from this encoding table we will fill these tables, and if we fill these tables we have defined GF8. Okay, so now what is 2 plus 2? Say 2 plus 2 we have to do. The first columns and rows are easily filled because 0 and 1s are identity. Now what is 2 plus 2? 2 plus 2 means x to the power 1 plus x to the power 1, which is 0. So next 2 plus 3. What is 2 plus 3? 2 plus 3 means 2 is x, 3 is x plus 1. So x plus x plus 1. So x plus x is 0. So 0 plus 1 is plus 1. What is, say, 2 plus 4? 2 plus 4 is x plus x square. So x plus x square means here, what is x plus x square? 6. So it is 2 plus 4 will be 6. 2 into 3. 2 is x. 3 is x plus 1. So x into x plus 1. So x square plus x. So it will be 6. 3 into 5. 3 into 5 is x plus 1. Now let's derive 3 into 5. 3 into 5, c. What is 3? 3 is x plus 1, the encoding. And 5 is x square plus 1. You see here. So this is x cube plus x square plus 1. So we can reduce this polynomial always. We can reduce the polynomial by subtracting a multiple of the generated polynomial. So x cube plus x square plus 1 we can reduce as, because the generator polynomial is the fundamental factor, we can always divide it by the generator polynomial, which is x cube plus x plus 1. If we divide, what we will get? We will get x square. And what is x square? X square is 4. Now with that we say that 3 into 5 is 4 in this field. So now let's fill one value. Let's say, let's do 4 into 3. This value. What will be this value? Please work it out. Here is the encoding table. Work out 4 into 3. Mr. Suresh.
Yes, sir.
Yes, please do 4 into 3 according to this table. If the polynomial is of the degree 3 or more, then you have to reduce by the multiples of the generator polynomial. What will be 3 into 4, right? What will be 3? 3 is which one? Which polynomial? 3 is which polynomial?
3 is the x cube.
No. 3 is x plus 1. You see this table, man. 3 is x plus 1 and 4 is x square. So you just multiply x square with x plus 1. See, I'll work out. Yeah. You just have to look at this table. 3 is equivalent to, here 3 does not mean the number 3. Here 3 is a symbol. Instead of 3, 1, 2, 3, 4, you can put ABCD, your choice. Here these are symbols, not numbers. These are not numbers. Do not confuse 1 as an element of the coefficient. Okay. So 3 is x plus 1, 4 is x square. 3 is x plus 1, 4 is x square. So just do 3.4. It is x square dot x plus 1. So it is x cube plus x square. Now what we have said, that if it is to the power 3 or more, we have to reduce by the multiples of the irreducible polynomial. So it is x cube minus if we do this will be x square minus, you can interchange with plus whenever you want, x square minus x minus 1. This is equivalent to x square plus x plus 1. So what is x square plus x plus 1 here? It is 7. So 3 into 4 is 7. In this GF8 under GF8. Okay, like this you have to do. Fine, that will be all for today. Galois field is finished. Next day we will do week 6. Next week, next Tuesday, this Tuesday, 4 days later. Okay. Thank you. Yes, tell me.
सर ये असाइनमेंट 4 के नंबर ऐड नहीं हुए हैं क्या? उसमें ऑनलाइन दिख नहीं रहे हैं।
असाइनमेंट 4 के
जो
असाइनमेंट 4
नंबर
के
क्वेश्चन के आंसर ओके
assignment 4 is a subjective assignment, so
मतलब
it
4
does.
अच्छा ओके
हाँ assignment 4 तो MATLAB कोड का ना, तो वो मैं अभी चेक कर रहा हूँ.
हाँ यस
So
सर
it will take some
ओके
time. Objective जितना fast नहीं result
ओके
होता है उसका, because objective तुम
ओके
जैसे ही submit करते हो तभी evaluate हो जाता है, but subjective तो मुझे करना होता है.
ओके सर ओके
But you can expect by 7th or 8th March. Okay.
ओके सर ओके थैंक यू ओके थैंक यू
हाँ.